taking here space to explain this all. Here, this is a nucleus. This is what? Nucleus. Around the nucleus, we know that electrons are present. That is general concept, basics everybody knows. Around the nucleus, electrons are present, that is common. But now we are proving that how this arrangement is there. How this arrangement is there. How electrons are outside the nucleus. How protons and remaining neutrons are inside the nucleus. We are discussing. I will show you perfectly. Listen. According to our data, once you see that, we'll take here only masses comparison. Only mass comparison. You know, once you see that, which of the following is heaviest particle? See this, I am writing about first neutron. Neutron mass is 1.675 into 10 to the power of minus 27 kgs. Isn't it? Where you can go for proton 1.672 into 10 to the power of minus 27 kgs. Isn't it? Where electron you can see 9.1 into 10 to the power of minus 31 kgs. Minus 31 means very, very less value. Isn't it? And here minus 27, you can compare this to minus 27, very close, we need to cancel. But remaining what? 1.675, 1.672. So this is 1.675, 1.672 means which is more? This is more. So after this what? New proton. Then what? Electron. That is a mass ratio of these fundamental particles. Mass ratio of this fundamental particle. So based on this mass ratio, you can take one best example to understand this concept. See, I am taking here a small general example for you. You take in a glass of water, glass of water. In this glass of water, you can take sugar. What you are taking? Sugar you are taking. Are you able to see this? Yes. I will adjust the camera. No problem. Yes. Sugar we are taking here. Sugar. Then what happens now? That sugar is dissolved in this glass of water. If it's not dissolved, we are taking a small glass rod or spoon. We are stirring. You are stirring well. What happened? Yes. After stirring well, the sugar is dissolved in water. The sugar is dissolved in water. When sugar is dissolved in water, a general example you can do at home and observe it. After dissolution of all sugar particles in the water, but a little bit small particles of sugar. What is the formula of sugar? Do you know what is the formula of sugar? Sugar C12H22O11. This is a formula of the sugar. That means it contains what? It contains carbon, it contains hydrogen, it contains oxygen, atoms, what we are discussing here. Okay, so that is this sugar when dissolved in water, after dissolution of all sugar particles, little bit, one or two particles are, we can see the bottom of the your glass or beaker. You can take any one. It may be glass or plastic glass. It should be transparent. Okay, it should be transparent. Then only you can observe perfectly. So that is here some sugar particles. What is there here? Sugar particles. Sugar particles are left back. Bottom of the, you can stir that like this. You can stirring the glass continuously, isn't it? Then what we can observe? The bottom of the The bottom of the glass, you can see little bit of undissolved, insoluble sugar particles are present. Bottom of the your beaker, bottom of the your glass. Why? Anybody can expect that? Why means compared to that solvent particle or water particle, the sugar particle's mass is more. The sugar particle mass is more. When we are stirring continuously, what happens? The mass is concentrated center of the or bottom of the glass. Mass is concentrated the bottom of the glass, that is center of the glass. That indicate here any particle which has more mass compared to other particles of water or dissolved particles of sugar. Dissolved particles of sugar and water. We can see three parts here. One part is what? One part is water. Second part is soluble particles, solvated particles we call. Another is insoluble particles. There are three parts. So insoluble particles are more mass compared to soluble particles compared to water. This is general observation what we see. That is based on this, we can see here the electrons, proton, neutrons also having similar to that of just what we take in glass of water. So you tell me which of the following is more mass here? Which of the following is more mass here? Tell me. Neutrons. Therefore, neutrons are first in the center of the nucleus. Then protons. So neutrons and protons are slightly different. That is 1.75, 1.72. That's not much difference. So we can say first neutrons, then protons, the remaining whatever are there here, electrons. So this is the position of fundamental particles in the atom. The position or location of fundamental particles in the atom. See, without any other examples, easily we can understand that what is the position of fundamental particle in the atom. You got clarity? Yes. What is that? So now tell me where electrons are present. Electrons are present inside the nucleus. Electrons are present outside the nucleus. Protons and neutrons are present inside the nucleus. Why these are inside? Why these are outside means simply we can say based on the mass. Based on the mass, we can easily understand which has more mass, it should be inside the nucleus, which is less mass, which is outside the nucleus. This is just general concept, but this concept is applicable. It is applicable to our remaining theories what we have. That is best example, Rutherford atomic model. You can see in Rutherford atomic model, what just now we discussed, according to same way, the fundamental particles are arranged, isn't it? How according to Rutherford atomic model, the nucleus, the word is introduced. The nucleus word is introduced. What is nucleus? What are nucleons? Nucleus means which has center. Which center what are present here? Neutrons plus protons. Outside the nucleus, what are present here? Electrons. We'll see a small introduction about our Rutherford atomic model. Clear? Shall I go for that? Yes. Listen, all of you. I will explain that. Yes. So, here we'll go for a small introduction about Rutherford atomic model. Rutherford atomic model. What is Rutherford atomic? You can see same as it is. I'm selecting. This is an atom. He selected gold foil. Now alpha rays. Alpha rays we are going to use to irradiate this one. Now sending through the, isn't it, small slit. These rays are coming towards this one. What happened? You see here, this is, you feel, nucleus. The rays are here from here onwards. Some rays are, we can see, pass through the atom like this. Some rays are pass through the atom like this, and like this, and like this. We can observe like this. And very few rays we can see are coming close to the nucleus and deflected. Coming close to the nucleus and deflected. Coming very close to the nucleus and deflected. Coming very close to the nucleus and deflected. Like this, some rays are. Very few rays are coming straight to the nucleus and going back. Only one ray. Only one ray. That is, for example, we can observe 3 conditions of observation. Are you able to see this? Yes, I will adjust the camera. See this? Yes, all of you see this. Here, first one is 3 observation. One is what? Most of the rays. Most of the rays. Which rays? Alpha rays. Most of the rays passed through the gold pile. That is first one. Second, some rays are deflected. And very few means 1 by 20,000. Out of 20,000, only one ray is bounce back with 180 degrees. These are the observations of our Rutherford atomic model, isn't it? You see now, whatever just now we explained, we can see here. First point we need to answer. We need to answer for first point. What is the answer for first point? We'll see. Just I will adjust the camera here. Yes, I will adjust the camera. See now, what is the first point here? Be careful. Understand this concept. Yes. What is the first point here? For first point, I am going to give answer for this. For first point. Why most of the rays are passed out? Because this atom, just now what we taken, this atom is very smaller. Already atom is very smaller. We know that is the smallest particle, we know. In that, we can see the nucleus is very smaller. Nucleus is very smaller. How much smaller means, you can see this is in a cricket stadium. In this, we are taking a ball, cricket ball. This is a cricket stadium, boundary, isn't it? In this boundary, we can observe one thing here. 5 kilometer distance from here to here. How much? 5 kilometer distance. 5 kilometers. How much is 5 kilometers? So from the 5 kilometers distance, we are observing this ball. How much small it is. From 95 meters or 100 meters, we can see that 6 and whatever it may 4 we are observed, but ball cannot seen in the stadium. But the radius of 5 kilometers, that is 5 kilometers of radius, how much smaller this ball in the stadium? 5 kilometers. Therefore, according to Rutherford, the most of the atom is empty. The atom remaining part of the nucleus empty. because more space is there. 5 kilometer distance means you can observe, you can understand. Example, I am ball from me 5 kilometers distance. From me 5 kilometer distance meet, you can understand how much distance. So from me 5 kilometer distance, remaining part is empty. Remaining part is what? Empty. So anybody can move. Anybody can move in the distance between me and last electron. Therefore, most of the rays are pass out because of empty space. That is the first point. So what we can understand, most of the atom is empty. Most of the atom is empty. Therefore, most of the alpha rays are pass out. You can understand here, isn't it? That is here electrons. Remaining part is smaller. Now, second concept. Some rays are deflected. Why some rays are deflected? What type of rays? Alpha rays are positive rays. Alpha rays are what type of rays? Positive rays. Therefore, the nucleus is also positive. Why? Just now we explained the charge of proton we know, that is plus 1.6 into 10 to the 4 of minus 19 coulombs plus 1.6 charge. But neutron no charge, 0. Therefore, the protons are inside the nucleus. They are positively charged, and our alpha ray is also positive. There is repulsion taking place. So when the rays is coming very close to the positive charge, positive and positive repulsion taking place. Therefore, the rays are deflected. That's the reason. So how many rays? Most of the rays are pass out, but very close to the nucleus, which ray is coming, that ray only deflected. Therefore, some rays, not all rays, some rays are deflected or deviated. Some rays are deflected and deviated. Don't forget this point. So that is the second answer is why some rays means nucleus is positive. Nucleus is positive and rays also positive. Therefore, positive repulsion taking place. Therefore, there is a deviation taking place. What we can understand here? Center of the nucleus. Center of the nucleus is a positive charge. Center of the nucleus is a positive charge. You see the position of fundamental particles. Protons and neutrons are inside the nucleus. Center of the nucleus is a positive charge. Therefore, the rays are deflected. Third point, you can see last point and third point of this. What is that? Very few rays are bounce back. Why very few? Very few means how many rays we sent here? 20,000 rays if we are going to send. Among this, only one ray is bounce back. 20,000 rays, out of the 20,000 rays, only one ray is bounce back means, you tell me how much smaller nucleus? How much smaller nucleus? According to Rutherford, it is a small ball from 5 kilometers radius, that much of small. That means alpha ray, one ray can coincide with this nucleus and strike. Therefore, it is positive and alpha ray is also positive. Therefore, it is not give chance to pass out through the nucleus. And it is bounce back. It bounce back how much? 180 degrees. How it is coming inside, same direction it bounce back. It's not deflected, it's not deviated, isn't it? It is moving same as it is back. Only one ray out of 20,000 rays. That means the smaller nucleus in an atom. Very smaller nucleus in an atom. So that understand this, only one ray means that is here nucleus is very smaller. Nucleus is very smaller. And you know already both are rays are positive, rays also positive and nucleus also positive. Therefore, there is a repulsion between alpha ray and nucleus, isn't it? So this is the position of a location of fundamental particles in an atom. Based on our own explanation, it is suitable to our theory. So like this, you can learn the chemistry easily. You can understand chemistry concepts. Otherwise, just you can by heart all these things, there is no use. So any concept you can own yourself. You can own yourself, take your own examples, understand the concept, then you never forget your whole life. Clear? See that glass of water just now we selected. All these sugar particles are center of the bottom of the your glass. Like this here, the center of the nucleus contain mass particles. Now you tell me what is the ratio of masses of fundamental particle means. You can give the simple answer. First one what? Neutron. Then what? Proton. Then what? Electron. So this is a ratio of mass of fundamental particles in an atom. So simply like this, we can understand every concept based on our own illustrations, own examples. So, and we need to apply our concepts to our theories. So don't learn your own concepts. It is not independent. Your concept is depend on your theories. Vice versa. Your theories are depend on your own examples. So that is a way to learn the any topic of chemistry. Okay, we'll see in next classes, isn't it? So like this, we'll discuss one by one. We'll go through that our own examples and also our concept. Then you feel good with chemistry. Okay, bye. And my introduction, I forget to give my introduction. I am Panaganti Rajesh Kumar. I worked in Narayana institutions for 15 years as a chemistry lecturer. I am handling both NEET and advanced, and also I am taking for mostly all type of classes in different institutions. So one more thing, my qualification is MSc B.Ed, and I'm qualified CSIR NET, and also qualified SET, and I am assistant professor qualification from Usmania University. Thank you very much.